Why is it?
We should all share. We do. Yeah. We just started like this. Easy as much. No, one's she's like turtle.
Okay, all right, that's worth it.
I'm also actually
I guess that's
good. And I'm losing one. This is me. Teach me your way. I love that. I'm going to invite.
fast though. Well, so 4-1 is negligible. 4-2 is pretty quick, and then 4-3 is what we're going to spend Monday on.
Got it. Do you have any tips for making sense of all like the difference, the overlap and the diagrams that we have for this?
Absolutely, it's one of the big things we're going to talk about in class today,
Excellent.
which is time to get started on now. So perfect timing.
We're excited for the outside class.
Yeah, so it seems. Let's see, why is the, I don't know why that said, oh, I already hit pause. Okay, time to get started. So I got everybody down for attendance. Yeah, so as you just noted, we have a pretty thin showing today. Everyone's coming outside, I guess, except for, and I understand some people have conflicts. And of course, really, there is something one could argue maybe kind of better about an in-class thing. So anyway, no problem. Everything's good. Yeah, so here's where we were last time. We were talking about surface independence. And I want to sort of start over with that, fresh start with this topic. But of course, we did talk about this last time. Here's the idea. If you have one curve and another curve that have the same boundaries. So in other words, they start at the same point, they end at the same point, right? Then there's this feature called path independence. Path independence says that if you look at the line integral over the one curve and you look at the line integral over the other curve, path independence says that those two line integrals are equal. Okay. So this is something we talked about a while ago, and we're not going to rehash the whole thing. I will remind you, though, that there's an alternative version, which is to say that if you kind of look at going all the way around like that's what you might call C1 minus C2. That line integral equivalently just needs to be 0. So take your pick. Now, for whatever it's worth, I mean, the definition as stated for path independence really, connects most naturally to the term path independence, because it's independent of which path you take. I mean, it really, very natural. Sometimes though, in proving theorems or connecting to other ideas, this other version is actually more useful. Sometimes, all exceptions granted. Anyway, be aware both formulations, they say effectively the same thing. Okay, so with that in mind, here's our equivalent notion of surface independence. If you have one surface, and I've deliberately laid this out on the page analogously, and I'm deliberately going to sort of walk through it analogously to underscore how it's the same idea. You have another surface, and if they have the same boundary, now the boundary now is no longer just a pair of points. Now the boundary is a curve, right? But if they have the same boundary, surface independence means that those two flux integrals are the same. Again, a property of the vector field, flux through the first surface, flux through the second surface, exactly the same thing. And now again, there's an alternative formulation. The alternative formulation is to say, well, these two integrals being these two integrals being equal is the same as saying that their difference is 0, and their difference is a flux through this kind of combined surface here. And so it's equivalent to say that closed flux integrals are 0. So now y'all know I'm a huge fan of analogies, and look how strong this is. This is a really, really strong analogy. This is literally just everything shifted one dimension up from the notion of path independence. And I'm actually going to be able to illustrate that another way on a couple of pages here. So in just a few minutes. Okay. All right. So that's what surface independence is. Oh yeah, question.
Can you explain what it means for a surface to be closed?
Yeah, it means that a couple different ways you could think about it. It means it doesn't have a boundary. Right. So in other words, if you have an open surface, then there's an edge, right? But when it closes up, right, that's the motivation for the term. Then the boundary has all kind of sort of disappeared. So that's one way to think about it. Another way to think about it is that it is a boundary of something else, just like a closed curve is a boundary of a two-dimensional region. So again, everything's one dimension up. So take a pick. They mean the same thing in effect. And there's some formalities and anomalies that I'm deliberately ignoring. Okay. Yeah. No worries. Okay. So just like now, y'all will recall with path independence, we use the fundamental theorem of line integrals to argue that every gradient was path independent. I'm going to argue here now that every curl is surface independent, and I'm going to argue that with Stokes's theorem. So Stokes's theorem says that I can evaluate fluxes with a line integral around the boundary. I can evaluate fluxes with a line integral around the boundary. These are two different surfaces, sure. We have the green surface versus the blue surface, totally different surfaces that we're computing fluxes, but they have the same boundary. And so they're computed by Stokes's theorem with the same line integral. And so they're the same, AKA this vector field is surface independent. So every curl is surface independent. Okay. And now again, harder to prove. We're not going to even try to how would one go about proving that it goes the other way also. Not only is every curl surface independent, but every surface independent is a curl. Certain regularity requirements, and again, I don't want to get into the weeds. Okay, so again, structurally kind of analogous, right? With path independence, it was gradients. With surface independence, it's curls. Weird coincidence. What are the odds? And again, I'm going to come back and talk about that later. Okay, here's another thing that's going to look familiar. Now, we talked about this last time, and I'm out of color, so I'm just going to have to duplicate some color. Where I'll use gray for these. Okay. We had previously 3 different equivalent formulations of path independence. Now here are effectively 3 independent formulations of surface independence. Why don't I zoom so we can see better? 3 formulations of surface independence. We also, I'm going to note that there are kind of 2 ways over here to say that, and bear with me, it's going to seem like this is coming out of nowhere for the moment. 2 different ways to say that the divergence is 0. I could say it right out and say the divergence is 0, or I could say the divergence is a function for which all triple integrals are always 0 no matter what domain you pick. And then come on, what could it possibly be, right? There's no function whose triple integrals are always 0 no matter what domain, right? Other than 0 itself. So these are equivalent statements in light gray. And the connection then between these 2 ideas and the way we get this, what I'm going to call a local test, just like we did for path independence twice. The way we make this connection is by way of this connection that closed fluxes. Gauss's theorem tells us closed fluxes are triple integrals of divergence. Right? And so that gives us this local test. I mean, all of these conditions over here, well, let's see, this condition is equivalent to that condition, and therefore everything, all 5 of the conditions that are written down here, are therefore all the same. And so our local test is, if you have yourself a vector field and you'd like to know, hey, is my vector field a curl of something? Does it have an anti-curl? More likely, is my vector field surface independent? Which is a really nice feature to have, and I'll show you why in a minute. You can decide on whether it's surface independent just by taking the divergence. Take the divergence, see if you get zero. If you get zero, then yeah, it's a curl, it's surface independent, go crazy. Does that make sense? Okay, and again, notice the layout on the page. I mean, doesn't it lay on, it looks exactly on the lay in terms of layout, exactly like the argument we made about local tests for gradients. And again, that's on purpose. Okay, so let's see an example of how this gets used. This is a really powerful example. By the way, the book doesn't really develop these ideas the way that I'm doing here. The book takes a different sort of what I'll call clunkier approach, which is fine. I've done it that way, the book's way in the past myself, but this is really much better, I think, my own opinion, right? Everybody's got their own opinions. But I think you'll like mine better than the book's version of this. And for one thing, they don't use the word surface independence. Anyway, so here's a question. And as usual, notice that our question doesn't give any immediate hints as to how to do it. It doesn't say use Stokes's theorem to compute this flux. It doesn't say use the divergence theorem or, you know, use a parameterization. It just says, look, here's this, compute the flux. I need you to do it. You decide how to do it, right? So what do we do? And we have various tools. 3 of which I just enumerated. Now let me show you how the fourth tool here, our surface independence, is really going to help us out here. So in particular, we start by looking at our vector field in the hopes that it might be surface independent. I'm going to go ahead and compute the divergence of it. Side note, I mean, there's multiple ways that the divergence could be useful. It might help me conclude about surface independence. It also might be the integrand for a triple integral, possibly, that I might compute. So, I mean, this is not a one motivation calculation. This is a couple different ways this could be useful. Okay, so we decide to compute the divergence, and the divergence is 0, and therefore this vector field is surface independent, which means that I can change to any other surface that I like. It's got to have the same boundary. Again, that's the stipulation. You know, I mean, it wouldn't be realistic to say I could choose literally any other surface. That's come on. That's not realistic. But as long as you've got the same boundary, pick any other surface you like and just change the surface because of this surface independence. Is that cool? All right. Cool. So let's start thinking about surfaces then. The surface that we have, our given surface, is part of an upside down elliptical paraboloid. Flashbacks to chapter 2. But specifically just the part above the XY plane, right? So our surface is this thing right here. Now, sticky wicket, do be careful with this. A lot of students get confused as to what exactly this surface is because they're like, okay, well, we've got this part here, but then we also have this part down here because don't you get that when you like cut it? And very importantly, no, this part here is not part of the surface. We're looking for a part of that paraboloid. These points down here are not on the paraboloid. Full stop. They're not there. When I say I want just the ones that have z greater than or equal to 0, I'm not saying also add in additional points, right? This is just purely an additional restriction on the original paraboloid. Right, so make sure to realize we're only talking about the paraboloid part here. We're not talking about the floor there at the bottom. Is everybody comfortable with that? Like I say, be really, really careful interpreting the question. I mean, the interpretation of the question makes a dramatic difference in how one answers the question. And if you misinterpret the question, then you're just not answering the question. It makes it, like I say, a tremendous difference. Okay, so that's a big warning. Do be super careful on that. Okay, so let's talk boundaries. My boundary is pretty clearly that curve. We have to worry, of course, about orientations. Notice that my original surface is, it says right here, oriented downward. In order to be able to compute a flux, you have to know what the orientation is of your surface, otherwise it's not a fully stated question. Oriented downward means that we're choosing, you know, I suppose you might call that the inward orientation. Again, you know, it's not really an inside or an outside, but anyway, that orientation as opposed to the other one. And remember, orientations are needed in order to do the right hand, you know, thumbs, fingers, swirls approach to orientations. And now you just have to do this geometrically with your own hand, but thumb in the direction of that normal vector, that makes a swirl that goes a certain way, and our orientation is this way. What do you think? Everybody's
Explain the rationale one more time. You put your thumb in the direction of the.
thumb in the direction of the surface normal, right? The surface normal defining the orientation. Then your fingers want to bend around a certain way. That defines what I like to call a swirl. And in this case, the swirl is going to look like, the hard thing here is I'm drawing it on the near side of the surface, not the back of the surface, right? But with that understood, the swirl is going to be like this. And how does that side swipe up against the boundary? This side swipes up against the boundary that way. Is that cool? Yeah, that's, you know, you really have to kind of think visually and use your hands. Right. Okay. Sure. Okay, so now we know what the orientation is on the boundary. Now we can reasonably ask the question, well, according to that, then what's my new surface, and what is the orientation I have to pick on my new surface? So you could probably see this coming. The new surface I'm going to pick is, well, yeah, let's pick the nice, easy, flat surface there in the middle. And now we get to play the game. Fooey on this top surface. We're done with this stuff, by the way. Now we don't need the original surface anymore. Bye S. You served your purpose. We no longer require you on the page, right? Now that we know what the boundary is, the oriented boundary, all I have to do is look at that boundary and ask which one of these possible orientations on that boundary gives me the correct orientation. I'm sorry, I misstated. Which one of these two possible orientations on my new surface, gives me this correct orientation on the boundary. So, you know, again, you got to think it through. You got to consider the possibilities. If it were up, then thumb, fingers, swirl, etc. And well, that would take me around the wrong way. It just doesn't work, right? Whereas if I orient this way, thumb down, look at the way that your finger turns. And that orients you the correct way, and thus that is the correct normal vector. What do you say? Everybody happy? It's all over with the shouting at this point. We have our new surface. And let's see here. So surface independence tells us that I can use my new surface S2 instead of the original surface S. Free for nothing? Well, low cost, right? I did have to compute the divergence, think about orientations, but got my new surface. My new surface is a totally new question to entertain. And how would I compute this flux through this new surface? Here you go. How would I compute that flux? And again, you got options. You know, you can think about Stokes's theorem or various different things, but don't forget sometimes you get geometrically lucky, and that's the big move here. The big move here is that my normal vector is a constant. It's simple. It's simple because my new surface is flat, right? So this awesome normal vector that I get to use is an immediate consequence of using surface independence. If I had kept my original surface, my normal vector would be all sorts of every which way, and I'd probably have to parameterize it, and it's a high effort situation. So easy normal vector makes for an easy dot product. The integral then turns out to be just that after you do the dot product, and I'll let y'all do the algebra there. the dot product is just minus xy, and that's 0 by symmetry. We're done here. Right? No parameterization necessary. No tedious computations. Very powerful method, right? And again, I wish the book would had. Hey, look, they have their approach. Their approach works functionally just as well. It's just less efficient and more confusing. But take a look, see what you think about their approach. I think you're going to like mine. Okay. So yeah. Summary. So somebody in the front asked me, about these diagrams, and here's a flashback. Here's our strategic diagram for R2. And remember, this kind of organizes ideas. This creates patterns. And we are now ready to talk about the equivalent organizing strategic diagram for R3. And here it is. Whoops. There we go. Strategic diagram for R3. Notice it's looks a lot alike. Now there's kind of, if you will, 3 different sort of, if you will, places on the diagram instead of 2, because we're in 3 dimensions instead of 2. So that's no surprise. That little bit. And I want to walk through and show you the various patterns that are in here. I'll start with the lifetime theorems. Exactness, as we discussed back in the 2-dimensional version. But if you have a gradient and you compute its curl, you get 0. And this works in both directions. If you have a gradient, the curl is 0. And furthermore, if you have a vector field whose curl is 0, it's a gradient of something. You have an anti-gradient. So that works both ways. And that fact works just as well here. Now it's curl instead of Green's operator. But here's the wonderful thing about these diagrams. Same statement, same argument also works here. So if you, oh gosh, what am I doing? Sorry. Yeah. If you have a curl, divergence is equal to 0. And furthermore, if you have a vector field for which divergence is 0, it's a curl of something. Said differently, it has an anti-curl. Now, the bad news about this little bit, you may have noticed, you might be having trouble remembering me telling you how to find anti-curls, and that's because I have not told you how to find anti-curls, because there isn't a good way to find anti-curls. It's algebraically, it's not something that's realistic. But sometimes simply knowing that it is a curl of something can be really useful. Okay. All right, so there's that pattern of exactness. Oh, likewise with boundaries, right? We've talked previously about how if a curve has boundary points, relates to whether that curve is the boundary of a surface. In particular, if you have a curve that's a boundary of a surface, if you think about it, now think about a surface, think about the boundary curve of that surface. It does not have any boundary points. Here, let me write this like this. Do it like this. Yeah. Oh, colors. If you have a curve that's a boundary of a surface, it does not have any boundary points. And vice versa. If you have a curve that does not have boundary points, then it's the boundary of a surface. Asterisk. There are some anomalous little weird cases that are peculiarities of being confined to 3 dimensions, and we don't need to worry about. So asterisk, full disclaimer, what I've just said is just ever so slightly a little bit of a lie, but there's nothing we need to worry about in this class. Okay, and again, the pattern moves right on over. So if you have a surface that does not have a boundary curve, this is what someone in the front was asking me earlier. If you have a surface that closes up, right, there is no boundary curve. Well, then it encloses a region. Therefore, it is the boundary of a region. And vice versa. If you have a, let's see, wait a second. Yeah, if you have a surface that is a boundary of a region, boundary of a solid region, there's no edge. You cannot sail off the surface of the earth because the surface of the earth is the boundary of a solid. See what I mean? There is no edge to sail off of. Okay. So this exactness is actually, there's a lot of different statements that are summarized. Of course, I like to phrase it as everything has a lifetime of two, right? But there's a lot going on with this, with that single phrase, however you want to say it. And the diagram does a really good job of sort of organizing. The critical thing to make all of this work is that these operators go in this order. That is critical. Make sure to get those operators in the correct order. Okay. All right. So let's talk about the accumulation theorems, our various different theorems that we've developed, fundamental theorem of line integrals, Stokes, Gauss, etc. Well, here's a way to think about the fundamental theorem of line integrals. If you have a function and you take its gradient field, if you have a curve and you look at its boundary points, then the change between those boundary points of the value of your original function is equal to the line integral around your original curve of the gradient vector field. So notice there's that pattern. There's like, you go this way on top and that way on the bottom, and the left side equals the right side. And that same pattern holds. If you just move it over, if I laid it out reasonably well, that's pretty close. Look at that. So same pattern holds. If you look at a vector field and you take its curl, if you look at a surface and you look at its boundary curve, then the circulation around that boundary curve of your original vector field is equal to the flux to the original surface of your curl field. Same exact pattern. So you see now why, I mean, I like to call these theorems by a sort of a grouping name. I call them accumulation theorems. Sometimes I call them boundary theorems. Sometimes I call them density theorems because they all have these same features. Because they're so, I mean, the pattern is overwhelming, right? And again, this is not a coincidence. The reason that that pattern is there is because all of these theorems are really the same theorem. They're literally all special cases of this very sophisticated theorem about differential forms that we're not prepared to talk about. So that's why the pattern's there. It's because they're literally the same theorem. So I think it's important to know that there is that connection, and it's also important to see all of these very strong analogies. And then likewise for the divergence theorem, yeah, that lays out pretty well too. So same exact pattern, and I'll let you all think through walking through that pattern as applied there. Okay, really good observation about the various relationships. And of course, this is a big vote for why it's good to understand strategic diagram. Okay, last thing I'm going to talk, oh gosh, last thing I'm going to talk about, path independence and surface independence and how they look on this diagram. Some of this I've already talked through. Y'all will recall, in fact, I'm going to zoom back in so we can see better. Y'all recall that we argued with the fundamental theorem of line integrals that when you have a gradient, that vector field that is a gradient must also be path independent in the sense that whenever you have two curves with the same boundary points, then the line integrals are equal. And the thing that makes this argument work, the way that we connected being a gradient to being path independent was with the fundamental theorem of line integrals. And, you know, pattern holding as strongly as it does, see if I can get that to lay well. Yeah, there you go. this is an equally accurate description of how we developed the idea of curls being surface independent, right? Curls are surface independent, and we used Stokes's theorem. Whoops. Stokes's theorem to justify that. Is that cool? All right. Okay, now related. Here's another thing we knew about path independent vector fields, namely vector fields for which any two curves with the same boundary point, you get the same value for the, okay, sure. Well, anyway, same value for the line integral. We knew that the curl was 0. Right, and what was the tool that made that work? Well, it was Stokes's theorem that made that work. And now compare to what we just did a minute ago, we argued that surface independent vector fields, I keep clicking to the pencil, surface independent vector fields have the feature that divergence is 0, and it was the Gauss's divergence theorem that argued that to be true. So one could make the case, right, that not only does it turn out that these arguments are really, really strong and really, really, the pattern is persistent, but you can actually use this pattern to help you come up with ideas. So for example, if you find yourself trying to remember, wait a minute, what's the, how do I connect, I mean, if I have a vector field that's path independent, I have a vector field that's surface independent, and what does that have to do with divergence? Okay, think about path independent vector fields, right? Think about what goes on over here, and whichever argument it is that fits in with that. And once you understand that argument, literally take the argument as it shows up on the diagram and just slide it over. And that will give you a very strong hint as to what the argument should be for surface independent vector fields. And amazingly, it's going to work. It always works. Okay, so I think that's really valuable. That's why I'm a big proponent of this diagram. The last thing I guess I'll say about the diagram is it actually helps you with ideas. So in particular, if you've been asked to compute a flux, here are the two places that fluxes show up. I must be looking at a vector field of this sort, whatever that means. I must be looking at a vector field where, hey, something interesting happens if I know something about the divergence. I should compute the divergence. Right? So it tells you exactly what to do. When you've been asked to compute a flux, compute the divergence. If you get not 0, right, then you know what your integrand is, possibly for use of Gauss's theorem, if you're going to go that route, right? On the other hand, if you get 0, then you know that there's the option of using Stokes's theorem. Note further, the diagram, if you've been asked to compute a flux, you must have been asked to compute a flux through some surface. Note the diagram tells you then, hey, think about the boundary curve of that surface. The diagram's telling you, right? And think about that boundary curve, and that might be, you might be able to use Stokes's theorem here. Or if you get 0 when you take the boundary, that hints to you by exactness that there is an anti-boundary region and that you can use the divergence theorem. So having all the ideas that we've talked about in this class sort of organized on this one diagram, this sort of organized chart, is just tremendous value, tremendous benefits. So for your consideration. All right. Okie dokie. So we are actually done for the moment with chapter 7. There are a bunch of examples that I put in the notes here to follow. These are intended as supplemental examples. I'm going to record discussions of all these supplemental examples this weekend, probably, theoretically today, but I'm not betting on it. And I'll post that, of course. It's going to automatically record on Zoom, but I will post those recordings very, very soon. And basically what we're going to do is we're going to use the diagram to come up with ideas of how we might be able to analyze various different questions about line integrals and surface integrals I'm going to talk it through, show you the thought process, and we're going to answer all 6 of I've got 6 examples in here that have various interesting twists and turns. Okay, all right, so that's coming. And now we move to chapter 4. So chapter 4, the couple of quick things I want to say about it. First of all, the book starts with 4.1. All right, as one does. But I actually think that the way that makes the most sense for me to cover the material is to actually start with what they call 4.2. So you're going to notice that while 4.1 is about Taylor series, I'm not going to say the word Taylor series for a while. Right. The other thing I'm going to say is these notes you'll notice are written a little bit differently. These are notes from my Math 212 class, and the way I'm going to cover the material is exactly the same, and so I'm using the exact same notes here. Being as they were written at a different time, they're also written in a different way, and we're actually going to move through these pages a lot faster because they're much less dense than the notes that I wrote for 219. Okay, so first observation. Single variable optimization. I'm going to loosely say it as we have different rules for how we deal with, possibly finding maxima in the interior versus the rules that we have for how to hunt for extrema on the boundary. In fact, the rules are in the interior, well, stuff about derivatives and differentiability and stuff like that. On the boundary, check them always. Right? You always check boundary points. You can quibble about the terminology of do we call them critical points? This is semantics, it doesn't matter. But you always have to check those boundary points as part of a complete process to try to find a maximum. Okay, so different rules. You don't need to check what the derivative is on the boundary. Okay, so analogously, there's different rules for interior and boundary when you're in 3 dimensions as well. In 2 dimensions or 3. So here's a region that has an interior and it has a boundary. And again, we're going to have different rules. The rules on the interior, that's going to be what we're going to talk about today. On the boundary, though, there's a couple of bits of bad news. On the one hand, the rules, the techniques we're going to find for how to deal with boundary critical points are different. That's one bit of bad news. And the second bit of bad news is I can't just say, check them, right? Because here, there's only 2 endpoints to a 1-dimensional interval. I can check 2 points. Just always check them, no problem. Here, there's infinitely many boundary points. I can't just check them. Right, so the boundary is actually going to be a really interesting discussion. That's going to be on Monday. But for the moment, right now, we're going to focus on the interior only, and don't worry about boundaries just now. Okay. So in single variable calculus, here's the rule. This is a review, so this is we're going to blow through this really fast. It's a process of elimination. I argue as follows: if I find a point like this, where the function's differentiable and the derivative is not 0, well, I mean, that means the function is in the process of increasing. Now, there's no way they could possibly be a max. It's just no way. Forget about it. It's increasing still. How could it be at a maximum if it's immediately bigger? Just move ever so slightly over to the right. Right. So this is our process of elimination. Our process of elimination, you'll notice, has 2 requirements. I need the function to be differentiable so that I can talk about derivatives and draw conclusions from derivatives. I also need for that derivative to be non-zero so that I can actually assert that it is in fact increasing one way or the other. Okay. All right. Now, keep in mind, again, this is a process of elimination. One of the big things students fail to understand about finding critical points is that we are not, converging, we're not following the clues and finding maxima. What we're doing is we are eliminating all other options except for hopefully a very small list. And then we're going to, well, by process of elimination, therefore it's got to be one of these. And so when you find a critical point, you don't really know anything about what's happening at that point. All you know is, I can't eliminate it. You're basically identifying our own incompetence, right? That's not a feature of the point. That's a feature of our method, right? So if you have a point that fails to satisfy this condition, all I know is I can't rule it out. I haven't got the slightest idea what's going on. If the point is a point where the function is not differentiable, no idea what's going on. Likewise, if the derivative is not non-zero, in other words, if it's zero, who knows what's going on. So don't make the mistake of thinking that these points are maxima, right? Just because the argument fails, that doesn't mean that the conclusion fails as well. It just means we don't know anything. And so always keep in mind these examples. Here is a point where f is not differentiable at this point, but it's also not a max. So that's not, that's a critical point. Sure, it's not a maximum. And likewise, here's a point where the derivative is zero. It's not a maximum. Okay. All right. Okay. Very, very similar argument that we're going to make in the multivariable case. Again, keep in mind, we're looking in interiors. Being as we are looking in the interior, we know in some sense that we have some room to move. We're not on the edge, so we can kind of move in whatever direction from that point we want. Yep.
So we're saying that's the domain of the function, right? So
Yep, that's right.
Be like a 3D function.
Yes, so here's our function. There's our function. You're right that the domain is over here, and then the target is over here. So yeah, the graph, I'm going to quibble with your lingo, the graph would be three-dimensional. That's right.
Right.
Yep. Well, correction.
But neither
The
of
graph
those
would
is
be
the
a
graph.
surface in 3 dimensions. Sorry, you were saying?
But neither of those is the graph.
Correct. We are not looking at a graph. It would just be hard to make sense. You know how 3-dimensional, it's hard to draw. Yeah. Okay. So here's our story. We know we're in the middle. We've got room to move. We can move whatever direction we want. Let's consider a scenario. I'm going to consider the scenario where the function is differentiable and the gradient is non-zero. What happens here? Well, if the function is differentiable and the gradient's non-zero, then this vector is telling me literally that the function is increasing, and it's also telling me in which direction it's increasing. Well, all I need to know is the function's increasing. It can't be a maximum. There's no way that's a maximum. Function's still getting bigger. Right? So process of elimination again. Now, again, notice the layout on the page, right, is deliberately, deliberately identical to the layout on the page here. Side note, okay, I did draw a graph. But in terms of the argument, identical argument. So we get the same sort of upshot then. So again, we can eliminate most points. Points where one of these conditions fails, namely points where either of these things happen, are our own failures. They're points where our method just doesn't cut it. It's where I don't know then, therefore, what's going on, because we cannot eliminate them. All you do when you're trying to find maxima is eliminate possibilities. Points that you can't eliminate, that's your problem, not their problem. We don't know anything about them. So again, I emphasize, and here's a couple of pictures. These are all critical points, and the classifications of critical points when you have more than one variable, it gets a lot more interesting, a lot more sort of varied. So here's the classical, there's a local max, right? Drawing a graph so we can visualize how it's a local max. But check it out. I mean, there's it could be an inflection point, or it could be a saddle point, or it could be what I like to call here a shoulder point, right? Looks kind of like someone's shoulder. So there's a lot of different possibilities. By the way, there's another, oh gosh, I should have pulled this up earlier, but you can amuse yourself by Googling, do a Google image search, monkey saddle. And you'll find two really fun things. One is you'll find a picture of a saddle that kind of curves down. See, our saddle here curves down in sort of two directions because we have two legs, and then it curves up in the front and up in the back. The monkey saddle curves down in three different directions, two legs and a tail. It's adorable, right? And then there's a picture of, if you do the Google image search, there's a picture of, somebody drew a little monkey sitting on his monkey saddle. It's hilarious. You'll also find in that same Google search a picture. Somebody put a little tiny monkey on top of a dog. It's pretty funny. Anyway, you can take a look at that. Okay. So a lot of different things that can happen. Okay, let's do it. Here's a function, two variables. And let's try to find critical points. Let's in the hopes of maybe finding maxima, right? But anyway, all we know how to do is to find critical points. Namely, we know how to find our own shortcomings, our own, the failure of our own system. So where does this function fail to be differentiable? It doesn't. It's a polynomial. Polynomials are differentiable everywhere. So I don't know if you want to call this good news or bad news, but there's no critical points. It's good news about the function. It's bad news about our search for maxima. So take your pick. But no critical points from differentiability. Next question, where is the gradient equal to 0? Okay, well, take the gradient. All right, take the gradient of that function. You get that. I need that to equal to 0 to find critical points. That gives me, you could call this a pair of equations or a system of equations. Think of it though literally as that's an equation and that's an equation. So this first equation here immediately tells me that x has to be either 1 or -1. And then this second equation, colors. Second equation immediately tells me that y has got to be 0, independent of whether x is 1 or -1. Doesn't matter what x is, y is definitely 0. And so put those two observations together, and what we get is 2 critical points. So those are our critical points. Is that cool? Yep.
So is a saddle like the three-dimensional
It has certain features in common, right? But I mean, I'll point out that the actual sort of inflection point picture looks kind of more like that, which you won't find on the saddle exactly, right? What you do have on the saddle is in some directions it's curving downward versus in other directions it's curving upward. And that's kind of analogous, sure. But don't worry too much about which one corresponds to which one, because ultimately it doesn't matter. Ultimately it's different, right? Because it's literally a different dimension. And so, yeah, they have common features, but there's just more ways in 3 dimensions that this can happen.
So that would just be if the partials had opposite.
No, that's deep water, surprisingly deep water. And that what you're thinking there doesn't work. So yeah, we're going to get to that. That's called the second derivative test, and it's more complicated for multivariable than single variable. Yeah. Okay. All right. So let's see, where am I, by the way? Yeah. Real quick, let me just point out that again, we found critical points, but don't over conclude. A lot of people will look at these and say, okay, well, one of these must be the max and one of them must be the min. False. Just not true at all. We don't have any idea if any of these are maxes or mins. They could both be saddles as far as we know. I mean, there's a lot of different weird surfaces out there, right? A question that we really don't know is even if we knew one of these was a local max, okay, well, yeah, but is it the global max? Is it the biggest value of the function anywhere? Oh my gosh, we have no earthly clue about that. And just to weird you out a little bit more, we don't even know if a global extremum exists. There might not be a maximum. There's plenty, I mean, look at a paraboloid. It doesn't stop, it just keeps getting bigger and bigger. There is no maximum. So there's a lot of questions that we don't know the answer to, and I'm going to point very quickly to this theorem that under certain conditions, if certain conditions are satisfied, then you can at least know that there is a global maximum somewhere, which is going to end up being a really useful fact that we'll talk about on Monday. Okay. All right. So let's see. Last thing for today, I think a realistic goal. Oh gosh, we have 15 seconds. Let me just point very quickly to the fact that there are different cases to consider sometimes. And so, you know, suppose you're doing an optimization, you take the gradient, set it equal to 0. Suppose you're looking at this. Just be aware that while it's tempting to look at x squared equals y squared and think that means x equals y, it doesn't. It is just as good as far as that equation is concerned for x to be negative y. And so what you have to do is you have to consider two separate cases. If you only consider the one case, then you've done half the problem. Right. And it's one of these, again, very frustrating things. It's tempting to say, oh, it was one algebra mistake. I mean, I guess you could say that. No, but it remains why you only did half the problem is one question, but the fact that you only did half the problem is pretty clear, right? So make sure to be really careful. You know, don't toss square roots around willy-nilly without thinking through the consequences, and always be on the lookout for, you know, this kind of business. Okay. All right, and we are out of time, so I'm gonna draw the line there and see y'all on Monday. Y'all have a great weekend.
Thank you.
Yeah. Okay.
So do we have any other problems after the one we